Hi, welcome to one and all. Next, we will be discussing about induced moduli and primitive characters. So let us go to the definition of an induced moduli. Before that, let us go to the previous theorem which we have studied in the last session. That is, let chi be a Dirichlet character mod k and assume that g of n chi is not equal to 0 for some n satisfying nk gcd of nk is greater than 1. Then there exists a divisor d of k d less than k such that chi of a is 1 whenever gcd of ak is equal to 1 and a is congruent to 1 mod k, 1 mod d. That means that if g of the Gauss sum g of n chi is not equal to 0 for some n satisfying gcd of nk is greater than 1, then we can find a d which is a divisor of k such that chi of a is equal to 1 whenever we assume we can find a such that gcd of ak is 1 as well as a is equal to 1 mod d. So if we can find such a d, then that d is called the induced moduli. So what is the induced moduli? It is, let chi be a Dirichlet character mod k and let d be a positive divisor of k. Then the number d is called the induced moduli for k if we have chi of a is equal to 1 whenever gcd of ak equal to 1 and a is equal to 1 mod d. This means that d is the induced moduli if the character chi mod k acts like a character mod d. That is, d should itself be a acts like a character mod d on the representatives of the residue class modulo 1 mod d, which are relatively prime to k. Note that k itself is always an induced modulus for chi. Let us see what we can take an example as you have already studied about Dirichlet characters. Let us consider the Dirichlet characters for k equal to 5. Here you could see that what are the Dirichlet characters. Chi1, there are 4 Dirichlet characters because phi of k is 4. So there are 4 Dirichlet characters. Chi1 of n, chi2 of n, chi3 of n, chi4 of n. And you all already know that these are in any order. You can write this in any order where chi1 of n is the principal character. Okay. Now if you could here you could see that if k is 5, let us take what is the meaning of k itself is always an induced moduli for k. Suppose you take k equal to 5, then we have to show that for if we take an a such that a is a gcd of a and k is 1 as well as a is equal to 1 mod d, then we have to show that chi of a is 1. For that, let k is 5. That means it is itself induced moduli for k. So for that, instead of d we have to take 5. Here a is any number, so here you have to take this condition because a is equal to 1 mod d, so you have to take a is equal to 1 mod 5. So that numbers are 6, 11, 16, etc. Now also this gcd of ak is 1. It is clear that is 6, 11, 16, etc. gcd is between these two numbers are 1. So if you take these numbers, you could see that since chi1 of n, chi2 of n, chi3 of n, etc. are periodic also, you could see that chi of 6 if you take, it is same as chi of 11 which is same as chi of 1. So it is 1. Evidently, thus for all such a this equation holds. So also clearly we can see that. So this is clear. I hope this is clear. Now also we can see that 1 is an induced moduli for k if only if chi is chi1. Chi is chi1, which is a principal character. Which is a principal character. You could see here that if 1 is an induced moduli, what is the definition? If 1 is an induced moduli, you could see that this is a equivalent to 1 mod 1 and gcd of 1 and k should be 1. So this is whether this is happen and this happens. This is chi of a is 1 only in the case if a we can take any integers in this case. If we are taking the induced modulus 1 as the induced modulus, then you could see that this this satisfies only when, see here, where for each k less than, each d less than k, that is for 1 2 3 4, for these numbers you could see that all these is 1 only in the case chi1. In other cases it is not 1. So that is why we can say that this chi is equal to chi1 in case, if chi is equal to chi1, then 1 is an induced modulus of chi. Or if 1 is an induced modulus of chi, this happens only in the case when chi is chi1. So that we can prove the theorem that let chi be a Dirichlet character mod k, then 1 is an induced modulus for chi if and only if chi is equal to chi1. So the proof is like that. If chi is equal to chi1, by definition, what is chi is equal to chi1? Chi is equal to chi1. In that case, for any a, we have chi of a is 1 for a relatively prime to k. In other cases, chi of a is, if a is not relatively prime to k, then in that case the value is 0. So you could see that a satisfies a is constant to 1 mod 1, because it is true for all integers. Then the number 1 is an induced moduli because it satisfies this condition 15. So you could see here now, so it is true for all a which satisfies these conditions. Chi of 1 is chi of a is 1. That is evident. So the converse part, you could see that if 1 is an induced modulus, then what is the definition? 1 is an induced modulus means we can find for any a the GCD of a and k is 1, and a is constant to 1 mod k, we have 1 mod d, we have chi of a is equal to 1. So this is possible. Chi of a is 1 only in the case when this chi is chi1. In other cases it is not 1. So it is, see, you can see it here, it is not 1. So that is satisfied only in the case chi is equal to chi1. So that is why we have to say that chi is equal to chi1, since chi vanishes on the numbers not prime to k. So thus we have came to a note that for any Dirichlet character mod k, the modulus k itself is an induced modulus, that we have seen in an example also. There are no other, we call that character as primitive. So what is a primitive character? When we say that a character is primitive, we say that a character is primitive when there is no other induced modulus for k. K is the only induced modulus and no other d. We cannot find a d which is an induced modulus. So that is the definition. So let us go to the definition of primitive character. The Dirichlet character chi mod k is said to be primitive mod k if it has no induced moduli d less than k. That is, chi is primitive mod k if and only if for every divisor d of k, for 0 less than d less than k, there exists an integer a constant to 1 mod d and GCD of ak is 1 such that chi of a is not equal to 1. If chi of a is equal to 1, then d is an induced modulus, and thus we can, if d is an induced modulus, then it is not primitive. If there is no induced modulus, then we say that Dirichlet character is primitive. So if k is greater than 1, the principal character chi1 is not primitive, since it has 1 as an induced modulus. So in case k is greater than 1, you could see if induced modulus 1 is an induced modulus only in the case chi is equal to chi1. So if chi is not chi1, chi is not chi1, then there is no induced modulus. 1 is not an induced modulus. So it is true for the prime cases. So let us see that theorem. Every non-principal character chi modulo a prime p is a primitive character mod p. This is what we have to prove. So for that, you could see that when we consider p is a prime number. So In case of prime number, what is a prime number? Which is divisible by only one and same number. So the only divisors if we can find a induced modulus, then that should be a divisor of that k. So here there are only two candidates. Either one is the 1 and the other one is p. So for p, that d less than p, we have to find another number which is less than d, which is less than p, which is an induced modulus. So here that such a character can be only one. Such candidate is only one. So, but one is not an induced modulus, because if one is an induced modulus, then that character will be the principal character. But here we are taking non-principal characters. Chi is a non-principal character. That is, chi is not equal to chi1. If chi is not equal to chi1, then divisor d is not an induced modulus. So chi has no induced modulus less than p. Only the next induced modulus is only p. So we can say that chi is primitive. I hope you understood this theorem. Next theorem is that chi be a primitive Dirichlet character mod k. Then we have to prove that g of n chi is equal to 0 for every n with nk is greater than 1. G of n chi is separable for every n. G of n chi, absolute value of g of n chi square is equal to k. This is quite simple, because in the previous theorem, that is, if g of n chi is not equal to 0 for some n with nk is greater than 1, then we have a theorem, theorem 8.12. What we have studied in that theorem is that we can find a divisor d such that chi of a is 1 whenever ak is gcd of ak is 1 and a is equal to 1 mod d. So by that we can see that this satisfies, that is, d is an induced modulus which is less than k. So chi cannot be primitive. So what is this assumption? This is possible only when g of n chi is not equal to 0. So this is because we have assumed a contrary, that g of n chi is not equal to 0. In that case, we can say that d is a induced modulus, so chi is not primitive. So in that case, our assumption was actually wrong. So g of n chi cannot be 0. Is not equal to 0 is not true. That is, g of n chi is equal to 0 for every n with the gcd of nk is greater than 1. So we have proved 1. Now, since if we have proved in the in theorem 8.10 that if g of nk is 0 for every n with the gcd of nk is greater than 1, then by theorem that Gauss sum is separable for every n. So clearly, so if this condition is satisfied, then g of nk is separable for every n. So that is proved. Now if Gauss sum g of nk is separable for every n, then by theorem 8.11 we have seen that g of 1 chi, absolute value of g of 1 chi the whole square is equal to k, which proves the third part. Thus we have seen that if chi is a primitive Dirichlet character mod k, then these conditions can be proved easily. So here we have observed that Gauss sum g of nk is separable if chi is primitive. If chi is primitive, then Gauss sum g of nk is separable. Later we will prove that g of nk is separable for every n, then chi is primitive. Now we have proved that if chi is primitive, then g of nk is separable. Later we will prove that g of nk is separable for every n, then chi is primitive, the opposite side. So that we will prove it later. Hope you have understood this properly. If you have any doubt, send me your comments and messages. Thank you for your patient listening.